Okay, we're going to continue on here. We're right in the middle of sort of titrations. We talked about several other types of titrations last time. We talked about titration of a weak acid with a strong base, like you did in lab the other day as well. And we also talked about titration of a strong acid with a weak base. Now, remember, those two sort of titration curves are pretty similar to each other. They basically have the same sort of 4 steps. Your kind of initial step before the equivalence point, after the equivalence point, and after the equivalence point. One difference is obviously in the case of the acid, weak acid titration, you're starting with an acid, so your pH curve is increasing in pH as you add the base. The other one, though, you're actually starting with an acid and you're starting with a base and you're adding an acid to it. So your pH starts higher and goes lower. But they're basically the same sort of problems along the way. And you were supposed to finish this example here at home, and hopefully you did. If not, I guess we'll do it together. So let's take a look at this example here. So in this titration, we're titrating 100 milliliters of 0.1 molar nitrous acid with 0.1 molar sodium hydroxide. So again, the setup in this titration is we are going to have our sodium hydroxide up in the burette, and we are going to add to it to the acid, which would be our nitrous acid here. We also see a Ka value for nitrous acid, which tells us it is a weak acid. So we are looking at a weak acid, strong base titration. So knowing that is helpful, as we talked about, because you should be able to sort of understand, what's going on, what type of titration or calculation that you're doing. We should end up really with a curve that will look something like this, perhaps, and our equivalence point there. So if we look at it here, we're going to start with part A of the question, which is, what is the pH of the initial solution before we begin the titration? So here, before we begin the titration, we pretty much have just the weak acid present. So because it's a weak acid and we want to figure out the pH, we will do really a weak acid problem in this case. So at part A here, before we basically begin, we have 100 milliliters of 0.1 molar nitrous acid. And again, we're reacting it with our 0.1 molar sodium hydroxide. In this case, though, because we have not really started the titration at all, that is pretty much what we got in the beaker. And we're going to use the Ka value that was given to us as well, which is, where's that thing? 4.5 times 10 to the minus 4. So because we haven't really technically added any sodium hydroxide here, we could do this ice table in molarity because we haven't changed the volume. So what we would want to do is basically our weak acid going to dissociate into H plus and NO2 minus. This will give us a Ka expression of H plus times NO2 minus divided by HNO2, and that obviously would equal our Ka value of 4.5 times 10 to the minus 4. So we're going to do an ice table, which frankly you can't really go too wrong with in a lot of cases here. This is going to be 0.1 molar. We're going to go zeros on these guys. Change here is going to be minus X plus X plus X, which means when we reach equilibrium, we got 0.1 minus X, X, and X. Any questions so far on the table here? So like normal at this point, what we're going to do is take our equilibrium line. We're going to stick it into our expression there. And we got a X squared basically divided by 0.1 minus X. equals 4.5 times 10 to the minus 4. Now, it is a small value of K, so we can make the assumption here, and we can assume, maybe, that X is equal to 0. And if you go through that assumption, you have 4.5 times 10 to the minus 4. We do that there, we will get 0.1 times 4.5 to the minus 4. We'll also take a little square root action of it. Going to give us an X value of 0.006708. Remember that we do want to check it. So to check it, we're going to divide it by what we were going to subtract it from. So we're going to divide it by 0.1, times it by 100 there to check. And in this case, we're going to be sad because it is about 6.7% in this case, which means that is not good, as that is over our 5% rule. So not so good here. So we do need to go back and really solve this using the quadratic formula, because it's above that sort of 5% threshold that we set. So coming back to this here, we're going to multiply everything on the bottom to the other side. So if we do that, that will give us x squared is equal to 0.00045 minus 4.5 times 10 to the minus 4x. We're going to combine everybody to the same side. That's going to give us an x squared plus 4.5 times 10 to the minus 4x minus 0.00045 is equal to 0 in this case. That obviously would be our A, B, and C in our quadratic, right? So that's our A, our B, and our C. So putting that into the formula, X would equal minus 4.5 times 10 to the minus 4 plus or minus. If you take care of everything inside the square root part, you will get something like 0.00018. Can't read my writing. 0802, I think. And if you take the square root of that, you will get 0.013423. That's all going to be divided by 2 times A, which would be 2 in that case. See how bad I did there. That was 4.5 to the minus 4 squared minus 4 times minus 0.000045. 180,203. I'm sorry, 203 there. So that should be like 203. Try that again there. All right, so that was 0.000180203. There we go. And square root it. All right, so now it's obviously going to give us 2 values for x. Doing the positive guy first, taking the minus 4.5 times 10 to the minus 4 plus the 0.01342 will give us an x value of 0.006487. Doing the negative, they're going to give us a negative 0.0069365. Clearly, in this case, we're looking for the pH, so we are looking for the H plus concentration, and obviously we cannot have a negative concentration, so that's not going to work for us. That would mean that in this case, this X value, we'll put a molarity there, and will equal the H plus concentration. So we're going to go into our pH here, minus the log of 0.006487. Gonna give us an opening pH here on our titration of 2.19. Yeah. Questions on any of those steps there? So again, a good reminder that you should make sure you do check your assumption. They will not always work. If you blew through the assumption there without checking it, you got 2.17, which technically would be incorrect in this case. You need to go back and solve it using, obviously, the quadratic. Any questions on any of those steps there? All right, so this is really like our opening pH of our solution before we really begin the titration. So in step B there, we're going to actually start the titration. So we're looking in step B, what are we going to have in terms of pH after we add 80 milliliters of the base to it? So we'll start B over here. So in B, we again are starting with 100 milliliters of 0.1 molar nitrous acid. In this case, we're adding 80 milliliters there of 0.1 molar sodium hydroxide. And obviously our Ka value is still going to roll the same. 4.5 times 10 to the minus 4 is our Ka. All right, so obviously we're starting the titration. So we want to make sure we do an ice table, and frankly, we do need moles. So we want to get the moles of everybody here. To get the moles, we're going to, for our acid, we're going to convert it into liters. We're going to use the molarity, 0.1 moles per liter. And that will tell us that in terms of the acid there, we got 0.01 moles of the acid. We'll do the same thing for our base. Once again, you can convert our volume into liters, divided by 1,000, times it by the molarity of our base, which is also 0.1 molar. And that would give us point, not that, point, come back. 0.08 times 0.1, going to give us 0.008 moles of our sodium hydroxide. All right, so now that we got the moles of everybody, we're going to do our reaction here. So this is going to be HNO2, which is our acid, going to react with our base. And do a acid base reaction here. So we're going to make a little sodium nitrite, and we're going to make some water. So basically a salt and water. So because we are obviously adding and we're doing the titration here, that is why we converted it to moles. We want to do this first ice table in moles. So for our acid, we got 0.01 moles. For our base, we got 0.008 moles, and we have 0 of this guy. So once again here, if you're not sure exactly where you're at, you probably have an idea based on the question, but again, that's what we're starting with, and this is what we're adding. And we are before, are we at the equivalence point, or are we after the equivalence point? In this case, we should be before the equivalence point. The moles of what we're adding is less than the moles of what we're starting with. So we're definitely before the equivalence point here. That also tells us in this case then that the sodium hydroxide should be the limiting reagent, and that should be the change that's going to occur here. It should get used up, 0.008 minus 0.008 and plus 0.008 here. That means at equilibrium, we're going to have 0.01 minus 0.008, 0.002 moles. That's going to be 0, and 0.008 moles. At this point, as we talked about, after you do this first ice table, you should convert it back to molarity using the total volume. So our total volume at this point is, we started with 100 of the acid, and we added 80 of the base. That's 180 milliliters. So we're going to convert each of these guys into molarity by dividing by 0.18 liters, which would be, again, our total volume at this point. And that's going to get us 0.002 divided by 0.18. Gives us 0.0111 molar. For our other guy, 0.008 divided by 0.180. Going to give us 0.0444 molar. Any questions on the ice table so far? Yeah. You can use millimoles if you want. It's fine. But moles is probably a good way to do it to make sure you don't mess up. But you can technically use millimoles and milliliters if you like, And that's what you get when you take milliliters times molarity, you get millimoles, basically. Other questions? So knowing that it is this type of titration, we should actually know what type of problem we have at this point. But just in case you do not know, you could also, once again, look at your ice table. And these are really the only two things that we got left over. And once again, you should be able to recognize that these two things are related to each other. That's again a weak base and really is conjugate base. I'm sorry, weak acid and is conjugate base. And that means that we are left with, as we would expect, a buffer in this situation. Yeah. So we are left with a buffer, which means at this point you have one of two options. You could either lay up another ice table if you chose to do so with the weak acid would be a way. Or again, probably the better move would be to go into our Henderson-Hasselbalch pKa plus the log of the base over the acid. We would want to figure out the pKa value here using our Ka. So that's the minus the log of the Ka. That's minus the log 4.5 times 10 to the minus 4. That's going to give us a pKa value here. Looks like 335. So the pH would be 3.35 plus the log. Obviously, this is the acid, which would mean that would be the base. So we want to go with that guy up on top, 0.0444 divided by 0.0111. So taking 0.0444 divided by 0.0111, taking a little log action of it and adding it to 3.35. Gets us a pH at this point in the titration there of 3.95. Yeah. Any questions on that there? It does make sense so far. Since we've added some base, our pH has gone up, right, from where we started with. Again, if for some reason it went down, you're definitely doing something wrong in terms of the calculation. Yeah. Any questions up to there? All right, so that brings us to the third part of the question, which I believe, if I'm not mistaken, is going to be the equivalence point. So we are looking for what the pH is at the equivalence point in this titration. So let's take a look at that part, which is C. Very good. Yeah. All right, so C, we're looking for our pH at the equivalence point of our 100 milliliters of 0.1 molar nitrous acid with our 0.1 molar sodium hydroxide. All right, so in this case, we're going to do our reaction, our HNO2. Our sodium hydroxide going to give us our same result there, our little sodium nitrite, and our water. All right, so if we roll into here, we obviously want to do it in moles. So 0.1 times 0.1 gives us our same starting moles for our acid of 0.01 moles. Now we're here to the sodium hydroxide. So there is a couple ways you could figure this out. So let's talk about a few different ways you could figure it out. It clearly did not give you a volume. The first thing that I should know is if I'm at the equivalence point, the number of moles of my sodium hydroxide should be what? Should be the same number, yeah, as what we have over there. So frankly, That's the quickest way to figure it out, what you need for the table at this point, which would be, it has to be the same number. Okay, so if I know it's the same number, and I know the molarity of the sodium hydroxide, I could also figure out the volume needed to reach there. So if I take the molarity, which is moles per liter, and I solve for liters, which is moles divided by molarity, I know that I'm going to end up with 0.1 moles of my sodium hydroxide. I know the molarity here is 0.1 moles per liter. And if I take 0.1 divided by 0.1, gives me, go. I missed a 0 there, didn't I? I did. That would probably be good if I put the 0 in there. Take 2. All right. So the moles is 0.01 moles. And the molarity is 0.1 moles per liter. All right, now try the right numbers. 0.01 divided by 0.1, going to give me 0.1 liters of sodium hydroxide is needed to reach the equivalence point. And that is basically 100 milliliters. Yeah, so it's basically how much volume you need to. The reason you need that is at some point you're going to need the total volume, right, to convert back into molarity. So you need to figure it out. So that is one way you can figure it out. Another way you can figure it out is it is a 1-to-1 relationship between these guys, which means you could use an M1 V1 equals M2 V2. This would be your acid information. That would be your base information. And you could solve for V2 in that case. You would take 100 times 0.1 and divide it by 0.1, which gives you 100 milliliters in this case. Lastly, the way you could do it is because it is a 1-to-1 relationship and because they both have the exact same concentration, you need the exact same amount to get there. So those are 3 different ways you could figure out how much volume to reach the equivalence point. Any questions on any of those ways? Yeah. So again, you do need to figure that out, how much volume to reach the equivalence point, so that when you do turn it back into molarity, you will have the right total volume. So again, a few different ways you can think about it. All right, so back to the problem. Now that we kind of figured out some of the important info here, we are going to zero out that guy. At this point, because we are at the equilibrium point or equivalence point, we would know we can't choose the wrong number because frankly, they're both the same number. So it's got to be that as the change. Keep wanting to miss that 0 there. That's going to be plus 0.1 moles here. That means when we reach equilibrium, we're going to have nothing here. We're going to have nothing here. And we will have 0.1 moles here. At this point, we do want to convert again back into molarity, and that is where our figuring out the volume to reach the equivalence point is important, because now we can see we had 100 milliliters of the acid. We needed to add 100 milliliters of the base to reach the equivalence point, which means our total volume at this point is going to be 200 milliliters to get there. And it means we're going to divide this guy by 0.2 liters to convert it back into molarity. We got 0.1 divided by 0.2, and that's going to get us a 0.5 molar. What's that? See, I don't like that 0. I just keep missing that 0 the whole time here, haven't I? I like miss it the whole way. Thank you very much. You are correct. It didn't get bigger there. All right. That 0 is going to be the end of me here today. All right, let's try this again. So that's 0.01. Thank you. 0.01. I missed it 4 times in this problem. All right, 0.01 divided by 0.2. That's going to give us 0.05 molar. Any questions up to there? Okay, at this point, if you're not sure what's going on, but frankly, because you know what type of titration is, you should be aware, but in case you're not, We can also use our ice table to help us out. We are left over with a salt at this point, and we know that this salt is going to go through hydrolysis. And we know that because basically this salt, bless you, is sodium ion and the nitrite ion. And the sodium we're not going to worry about because, as we talked about a number of times, it is neutral. But our nitrite ion here obviously comes from this weak acid. And remember that because it comes from a weak acid, it will continue on and go through hydrolysis. So really the next ice table that we're going to have is going to be these two guys starting to react with each other. And we're going to take NO2 minus, we're going to react it with some water. And also, if you're not sure what's going to happen, you should probably be able to figure it out from just looking at it. But they came from an acid, which means this guy over here is going to act as a base, which means when it reacts with water, it's going to act as a base. And that means it's going to accept the H plus. Obviously, don't overlook the obvious. It doesn't have an H to give, so it cannot give it away. So it's got to accept it in that case. The result of that is we're going to form always where it came from, and we're going to form a little hydroxide action. That means once again here, without finishing the calculation, we should know we should end up with a basic pH as we're producing hydroxide in this case. We're going to ice table this with our molarity, which hopefully is correct at this point. We're going to carry down our molarity from the equilibrium line, and that will be our starting molarity here. The rest of these are going to be zeros and X's in this table. That means we got 0.05 minus X, X, and X. This is going to go into our K expression here, which is again our products over our reactants. And by the way, this is what type of K? A, B, C, D, F, G. It is a KB. And I know it's a KB, and I know it should be using a KB because I have hydroxide there on the product side. So again, whenever you got that hydroxide on the product side, KB is what you need to be using. If you have that H3O plus or H plus on the product side, then KH is what you should be using. That means we do need to kind of flip our Ka value that was given to us. So our KB in this case would equal our KW divided by our Ka. So our KB would be 1 times 10 to the minus 14, which is KW, divided by our Ka, and that was 4.5 to the minus 4, I think. 4.5 times 10 to the minus 4. That is going to give us a KB value here. Lots of twos. 2.2 times 10 to the minus 11. So in this case, we're going to put in our numbers, going to give us X squared divided by 0.05 minus X equals 2.2 times 10 to the minus 11. I am going to assume X is equal to 0 here. That will give us X squared over 0.05 equals 2.2 times 10 to the minus 11. And that's good. I'm going to multiply that to the other side and take the square root of it. So times 0.05 and a little square root. Going to give me looks like an X value here of, we'll call it 1.054 times 10 to the minus 6. We do want to check it. So once again, to check it in this case, we're going to divide it by 0.05 and times it by 100. And I think we should be good. So divided by 0.05 times it by 100. It's not even 0.1%. So we are good in this case in terms of the check. It's good. All right, so because that is good, if we go back to our table, it's also important to remember that the X value here is actually our OH minus concentration. So we're going to go into the POH first. So this equals the OH minus concentration. So the POH here minus the log of, get rid of some of that there. Minus the log of 1.054 times 10 to the minus 6, going to get us looks like a 598. Now, again, if for some reason you felt that was the pH, it should not make sense to you, obviously, since it is would be acidic pH. To get to the pH, though, obviously, we're going to take 14 minus that number there of 598, and that's going to give us an 8.02, which is a basic pH and does make sense. As we would expect in a titration of a weak acid with a strong base, when we reach the equivalence point, it should be basic because we do have that salt going through hydrolysis and producing hydroxide. Any questions on any of those parts there? All right, the last part of the titration is after we add 105 milliliters of the base. So clearly we just did the equivalence point, and that was at 100 milliliters. So at 105 milliliters, we are going to be obviously past the equivalence point in this case. So we will pick it up at that point. So D here is after 105 milliliters of 0.1 molar sodium hydroxide is added to our 100 milliliters of 0.1 molar nitrous acid. All right. Okay, so we'll do our same reaction as we know we need to do it. And obviously we do need to do everything in moles here. So we'll start with our acid, which still should be the same. So we're going to initially start with 0.01 moles. For our sodium hydroxide, it's going to be 0.105 times 0.1. Going to give us 0.0105 moles and 0 here. And obviously we are after the equivalence point in this part of the titration. So as we should know, again, after the equivalence point, we're really just dumping excess amount of base in this case. So our base actually now becomes like the excess reagent, and it's going to be actually our acid here that is limited because we have plenty of the base to take care of it. That means the change here should actually be the acid. So you remember, you do not want a negative number change there, or end up with a negative number. So that is at this point going to zero out our acid. We'll have our 0.0105 minus 0.01 moles and 0.01 moles, this guy. Our total volume at this point is, again, we started with 100 milliliters of the acid. In this case, we added 105 milliliters of the base. That's going to give us a total volume of 205 milliliters, which we could use to convert these guys back into molarity. And that would get us 0.0005 divided by 0.205. 0.002439 and 0.01 divided by 0.205. 0.04878. So we're going to look at what we got left based on our ice table here. We have a salt and we do have our sodium hydroxide. As we saw in the previous step, that salt will go through hydrolysis and produce hydroxide. But as we've talked about before, in comparison of it acting as a base versus sodium hydroxide, which is a strong base, at this point in this titration, and you visually did this the other day in all those titrations. You just kept adding sodium hydroxide past the equivalence point. The sodium hydroxide is going to be a much major contributor to the pH. So it is at this point where we ignore any contribution from the salt and we go with all of it coming from the strong base here. And because that is sodium hydroxide, that means that that really is the hydroxide concentration at this point. And we could go into our POH. And if we do that there, minus the log of 0.002439, going to give us a POH of 2.61. We want to get to the pH by taking our 14 minus that. Going to hit 1139 on the pH. Which is definitely basic and what we would expect to be happening here past the equivalence point, because again, at this point, you're just dumping base in there and producing a lot of hydroxides really quickly. Any questions on any part of those titrations parts that we calculated? So as we talked about before, it is helpful for a lot of people to understand where you are in the titration curve, what type of titration it is, because frankly, like I said, you pretty much should know what type of problem you should be doing at those different points along the way. Any questions on titrations or how to calculate all that stuff there? All right, then to finish up the rest of this chapter here, we're going to talk a little bit about indicators, which we might have talked about before, but an acid-base indicator is oftentimes used to indicate a change, and it'll be a change in color. And usually when you use them for titration purposes, you do want the indicator really to change color near the equivalence point, because it's really used to indicate to you that you should stop your titration. Obviously not in the titrations like we did are doing currently, because we're taking the entire curve, but it does usually is used to stop there at the equivalence point. Indicators are really like weak acids. They have a protonated form and a deprotonated form where the H plus comes off. And really, depending on the ratio of the acid form of the indicator to the base formed indicator, it will be really what color you will see in the solution at that point. So really, if you have a sort of larger value of the acid version of it, the color of it in acidic solutions will predominate, and vice versa. If you have really a greater amount of the deprotonated form of it, the base version will. So most indicators work over a specific pH range, and through that pH range, you do see that sort of color change. So here are some like crystal violet, kind of yellowish there, bluish over there. There's our phenolphthalein, which we're interested in or have used before, really colorless there in the 8-ish range. And mid-8 starts to get that really faint pink to pH of 10, where you get that really dark pink. So it's really important to understand what indicator would be good for your type of titration, and not all indicators would be really good depending on where your equivalence point is. So when we have a strong acid, strong base titration, the equivalence point should be around 7, right? So you would want one where you would see some type of change in color around 7. We know weak acid, strong base is going to be a pH of basic around the equivalence point. So again, you would want one that would change color around there. And the strong acid, weak base titration is more acidic, usually around the equivalence point. So you would want one there. You could do a theoretical calculation based on the concentration of your acid and base at the equivalence point, what the pH should be, and you could choose really the most appropriate one. But again, you want to choose one where you would see an actual sort of change in the color, not that it kind of stays the color all the way through, so you don't get that indication that you need. So for example, here, if we did sort of like the titration we were just sort of talking about there, with nitrous acid and potassium hydroxide, which ones on the list here would be a good choice for an indicator? So let's take a look. So let's first talk about this titration. So nitrous acid is the one we just did. That is what type of acid? It is a weak acid, right? And obviously potassium hydroxide is a strong base, right? So just from that information, we know that when we lay up our curve and do our titration, the equivalence point, should it be acidic, neutral, or basic? What was it in the example we just did at the equivalence point? 8.02, yeah? So it should be basic. And it should always be basic when you have a weak acid and a strong base because of that salt going through hydrolysis. So that automatically, knowing that it should be basic above 7, means that we could eliminate a lot of indicators here that would probably not work very well for you, since pretty much thymol blue here works between a pH range of 1.2 and 2.8. That's going to change color like way before you're ready for it to do it, right? Same thing here, that is still acidic, so that's not going to work so well. Still acidic here for methyl orange. Same thing for methyl red, getting closer to neutral, but still acidic at that point. So definitely our equivalence point is going to change in the basic range. So that would not be a good choice. That guy would probably not be a good choice either. Now, this does get into the basic range, this one, but would it be a good choice, you think? It would not. Just if you kind of roughly think about the one we just did, it changed in the 8-ish range, right? Which means by 7.6, it's probably going to be blue already. Yeah. And that's not going to give you an indication to stop. So probably the two that might be good would be these two in this type of titration. 7.2 to 8.8. Again, that gets you into a little bit of the basic range, so that might work. And obviously phenolphthalein, which goes from 8 to 10, and you got that gradual change really around 8 point something. It'll kind of start changing into pink, is going to work really well. So based on the type of titration that you're doing and where you would anticipate the equivalence point being, you could pick an appropriate indicator. And like I said, if you actually have some numbers, you could do a quick calculation at the equivalence point and get a pretty narrowed down of where it should be changing to choose something that would be good. Would these two indicators be good for a titration of our ammonia and HCl? So again, the HCl being added to the ammonia. Would I want to choose phenolphthalein for that titration? I would not, because this is a case of a weak base and a strong acid, which means at the equivalence point, we will have hydrolysis happening, but it will be acidic because it will be producing H3O plus. So we would want something maybe in the acidic range here that would be obviously a much better choice for us to do it. So that's really what you want to look at, is where that equivalence point is going to be, what range you're kind of thinking is going to change color and kind of reach the equivalence point, and find an indicator that will hopefully have an actual color change within that range. Any questions on how to pick a indicator? It's about something. There we go. All right, so chapter 15 is about two more sort of equilibrium sort of conditions, and that is KSP and KF. And KSP, we talked a little bit about in some of the earlier labs. KSP is the solubility product. It is, as we will talk about, pretty much an equilibrium constant for things that are insoluble. So these are things that typically we think of as being insoluble in solids, and that's what KSPs are for. KFs, as we will talk about as well, are for complex ions. So that is the equilibrium constant for complex ions. KF is the formation constant, is what F stands for. And it's a formation really of a complex ion. They are, as we will see and sort of talk about, kind of two extremes in terms of their typical numbers. Typically, KSP guys are really small values. And typically KF guys are really large values. So it's kind of two different extremes in terms of the values as you typically see here. So we're going to start with KSP, which is the solubility product. So something, for example, like silver chloride, if you remember your solubility rules, which I'm sure you do, right? So your solubility rules will tell you, and you should know from group 1 experiment that we did, chlorides are soluble along with bromides, iodides. They're soluble in everything except for 3 things, which is silver, lead, and mercury 1. So based on solubility rules, we would expect silver chloride to be a solid. Now, just because solubility rules tell us that when you put silver and chloride together, you get a solid, there are actually a lot of factors that come into play as to whether or not you will actually see the solid form. Things like pH, things like concentration of the ions, and we're going to talk about that, bless you, in this chapter. They all come into play as to whether or not you'll see it. So sometimes after, the first semester and you talk about solubility rules, you feel like, well, it's always going to be solid no matter what the situation. Whenever we throw those 2 things together, we should always see a solid. But there are always a lot of factors that can play into effect and actually prevent you from seeing it. When we write equilibrium for solubility here and things that are typically insoluble, this is the general setup of how it's always written. And what I mean by that is left-hand side of the arrow are pretty much always our solids. And on the right-hand side of the arrow are always our aqueous ions, basically. So you always have like the solid going to the aqueous ions. Now, just because something is technically insoluble based on solubility rules, everything has some degree of solubility, even if it's like super small, like barely anything there. So we can set up an equilibrium reaction like we see for silver chloride, where it does break apart into a silver ion and a chloride ion. And we could write an equilibrium expression for it, how we normally do, which would be products over reactants. In pretty much all cases with KSP, the reactants are always going to be solid. So what they end up being is really just the products is what's included in the expression. So this is just like our products over reactants, except our reactants are always going to be solid. So the KSP here is the concentration of silver times the concentration of chloride. We still do everything that we normally would do. So if there's some coefficients in front of the ions, you put them into your expression. So when we have something like magnesium fluoride, breaks apart into 1 magnesium ion and 2 fluoride ions. The KSP is magnesium times fluoride, and we would square it because of the coefficient, just like normal. And once again, this is a solid on the left, so we would not include it. Silver carbonate breaks up into a couple of silvers and a carbonate. And once again, the 2 here gets incorporated into the KSP expression, and that's calcium phosphate, which gets incorporated, both of those guys, into the expression. So one kind of different thing about KSP is, even though it's still an equilibrium constant, it's still the same kind of deal. Pretty much it's always solid on the reactant side, so it's always usually just your products. One way that we could look at as to whether or not we would expect a precipitate to form if we kind of put some ions together is we could actually calculate Q. And Q here is the same thing that we did earlier. It's the reaction quotient, and it's calculated the exact same way. So if I wanted to calculate Q for silver chloride, Q would equal the concentration of silver times the concentration of chloride. So it's basically the exact same way. If I wanted to do it for this guy, Q would equal the concentration of magnesium ions and the fluoride ions squared. So just like Q we used earlier is calculated the exact same way as K, same deal here. And we could use Q and compare it to the KSP value to help us decide whether or not a precipitate will form. If you calculate Q and it's less than the KSP, you have what is known as an unsaturated solution. Unsaturated solution means you have not hit the maximum amount of solute that will dissolve, which means the solute will continue to dissolve. And you would expect no precipitate to form. So if you compare Q to the KSP and it's less than, no precipitate. If you compare Q and it's equal to the KSP, you have a saturated solution. So typically a saturated solution is a solution where you have hit what is sometimes referred to as the saturation point, the exact spot where you've hit the maximum amount of solute that will dissolve at a given temperature. So at that point, it will all dissolve, but if you put just a little bit more in, no more is going to dissolve, right? So you're basically at the tipping point to going into not going to dissolve anymore, and you would see a solid. If you calculate Q that is greater than the KSP value, that means you have a supersaturated solution. And a supersaturated solution is a solution that you have way too much solute dissolved, which means it wants to come out of solution. And you would expect a precipitate to form. So we can use Q like we did earlier to help us understand, are we at equilibrium? But in this case, we're going to use Q to help us understand, do we expect a solid to form or not to form if we kind of dump these ions together to solutions that contain ions? Any questions on that there? So these are some KSP values. You have a similar table in your book and you should memorize them all. No, I'm just kidding. But what you will see if you look at a lot of these values, or the values that are in your book, is a lot of them are really, really small values. There's like minus 36, minus 49, minus 29. So KSP values are really, really small. And because they're really small, that means when we reach equilibrium, would we mainly have reactants or products? If the KSP value is small, which is an equilibrium constant value that's small, you should mainly have reactants or products. Small value of K means anyone? Small value of K would mean reactants. Yeah. So in order to have a small value K, you need more reactants than products, right? So K products over reactants. So because they're really small, pretty much most of it lies over here on the solid side and all these guys. But again, there's still a little bit of it that will break apart into the ions and will set up an equilibrium. But because they're really, really small values of K, we expect it really to be kind of insoluble, like we follow the solubility rules in most cases. All right. So when we do solubility type problems, there's really kind of two sort of problems that you have to come across and do. And one, you really should do an ice table. The other one, you don't have to do an ice table, but it can help you sort of figure out what's going on. So let's talk about a couple of different versions of solubility and that you're sometimes asked for. One is the molar solubility, and that is, I guess, a fancy way of saying molarity. Yes. So if you're asked for the molar solubility of something, you're really asking for what is the molarity of those guys in the solution. And that it would be molarity. The other solubility is how many grams per liter, which sometimes is a more useful sort of unit because we can figure out, how many grams will dissolve or how many grams won't dissolve. And these two are related to each other, right? And if I have moles per liter and I want to go to grams per liter, what is the thing that I use to go between those two? How do I go between grams and moles? Or moles and grams? Not everybody at once. That is the molar mass from the periodic table. Yeah. So the molar mass from the periodic table is the one that basically ties those two things together. If you need to kind of convert from molar solubility to solubility in grams per liter or vice versa, the molar mass from the periodic table is what you would want to use. Now, in one case, one type of solubility problem is one where you're actually asked to calculate what the KSP is. And in that situation, you would find the solubility of the compound. You would find basically the molar solubility of it. You would find the molar solubility of the ions. You would put it into the KSP expression and basically solve for the value of KSP. The other type of problem is one where you're just given the KSP and you want to know what is the solubility of everybody there, the ions that are floating around in the solution. In that case, typically an ice table is what you would use. You would use an ice table, and then that would allow you to solve for the solubility of each of the ions. So those are the two sort of problems very commonly found in KSP. Either you're solving for the KSP or you're given just the KSP and nothing else really in a lot of cases. So let's take a look at one and kind of see how it works here. So the solubility of silver phosphate at 25 degrees is 1.6 times 10 to the minus 5. What is the KSP for silver phosphate at 25 degrees Celsius? I'm not sure why all the spacing is like that. Dramatic pausing, I think. So in this type of case, we're actually looking for the KSP, which technically speaking, you don't really need to do an ice table, but I'm going to do an ice table to sort of show you it. So hopefully you have a better understanding. So clearly, if we're looking for a KSP, we can make a pretty safe assumption that this guy here is going to be a solid, and that's where we're going to start with. It's going to break apart into its ions, which in this case would be 3 silver ions and 1 phosphate ion. Questions on that part there? By the way, now that I have the equation, my KSP expression should be the concentration of silver that is cubed times the concentration of phosphate. And once again, our reactant side is a solid, so we don't include it in there. Okay. So I'm going to show you the way that we typically would do an ice table. And again, you don't necessarily have to do this part for this type of problem, but again, it might help understanding here. So if we were to roll an ice table here, we would initially start with 0 of everybody here on our product side. We're not going to worry about the solid on the left because frankly, it's a solid, so it's not going to find itself into anything, although we are going to relate everything sort of back to it at some point. Now, in this case, the change is going to be like normal. We normally would have some minuses happening on this side, right? And on the other side, we would have some pluses. Now, typically speaking, when you do sort of KSP type problems, although we've used X's for everything at this point, and you could, if you wanted to, still use X's, people will oftentimes use a different letter in the ice table, and they will oftentimes use S. So instead of X in the table, a lot of times people will use S. And what S stands for is the molar solubility. It basically is the molarity. So people will use S in these type of situations rather than X. Again, you can use any letter you want, but that's what most people do. We still need to do everything that we normally would do, which means we also need to make sure we take into account the coefficients like normal. So this would be plus 3S, and this would be plus S at this point. That means that when we get to equilibrium, this would be 3S, and that would be S. And let's get any questions sort of on the table. Yeah. Now, normally what we would do, right, is take that equilibrium line and stick it into our equilibrium expression. So if we did that just like we normally would do, where our KSP is equal to the silver concentration cubed and the phosphate, that would give us basically 3S cubed times S. Yeah. In this particular case, we're actually looking for the KSP value. So obviously, if we were given the KSP value, we could be able to solve for S in this case. We don't really need to solve for S because what was given to us in the problem right here is the solubility of this guy is 1.6 times 10 to the minus 5. That right there is S. That is the molar solubility, right? So that number right there is the molar solubility, which means that is that S and that is that S right there. So we could put it into here and go 3 times 1.6 times 10 to the minus 5, and we still need to cube it, times 1.6 times 10 to the minus 5. And if we do that there, we will end up with 1.8 times 10 to the minus 18 as our KSP value. Is that a large value or a small value? is a small value, which would mean we mainly have reactants at equilibrium, which means in this case, we would mainly have the things still together, right? It would be basically insoluble, most of it. It basically means in terms of phosphate, we only got out about 1.8 times 10 to minus 18 molar basically of it. And for silver, we had a little bit better on that, but not very much is in there. Question on that. Now, I say you don't necessarily have to do an ice table in this case if you understand molarity and how it breaks apart into ions. In this particular case, basically, if you understood that the concentration of the silver phosphate was 1.6 times 10 to the minus 5 molar, and the 3 silvers and the 1 phosphate over here, that it is a 1 to 3 relationship. You take 3 times 1.6 times 10 to the minus 5, and that is a 1 to 1 relationship between those guys, which means it's 1.6 times 10 to the minus 5. That is essentially what we just did here. So the ice table kind of walks you through making sure you don't miss the, I need to multiply by 3 and also cube it. And that's a very common mistake that some people make is, like, I multiplied it by 3, I still need to cube it, so they kind of hesitate or second guess themselves. So if you want, even in a problem like this where you wouldn't necessarily have to do it, you could have just kind of figured out the concentration of each of those ions and then just stuck it basically right into there. You would have the answer at that point. You could do that, or you could do the ice table that will kind of lay it out for you and kind of take you step by step through it. Any questions on that there? All right, well, I did one, so you should do one probably. Let's do, what is the solubility of silver chloride in grams per liter? I'll get you some molar masses here in a second. KSP of it, 1.6 times 10 to the minus 10. Okay, let's take a look. So we should start with silver chloride. So that is AgCl. We have a KSP value, so we know that that's insoluble in case you didn't. So we would want to start perhaps with our ice table in this case. So once again, the solid's going to be on the left. It's going to break apart into its ions on the right, which would be a silver and a chloride in this case. Our KSP expression would be the silver times the chloride, and that would equal our number that we got going on right there in this case. So in a situation, a KSP problem where pretty much that's all you're given is like the formula and maybe the KSP value, you might have to go look it up in a table sometimes. You definitely want to go the ice table approach is probably the best way to do it. So initially here, we're going to ignore the solid because frankly, it's a solid. We're going to start with zeros of these guys. Change is going to be plus S and plus S. Again, each of the coefficients here are 1. That means at equilibrium here, we would have S and S. Any questions on the ice table here? So very much like all the other ice tables, we're going to take our equilibrium line and we're going to put it into our expression. And that means that the KSP here would equal S times S, and that would equal 1.6 times 10 to the minus 10. That gives me an S squared is equal to 1.6 times 10 to the minus 10. I just need to do a little square root action on both sides, to solve for it. Square root of 1.6 to the minus 10 going to give us an S value of 1.26 times 10, 1, 2, 3, 4, 5, minus 5 in this case, Any questions on that there? So that S again represents the molar solubility. So this would be really the molar solubility of silver chloride in this case. It also is obviously the molar solubility of the chloride ions at equilibrium. it is also the molar solubility of the silver ions at equilibrium. And how come it is also the molar solubility of this guy? If we were to go from the molarity of silver to the molarity of silver chloride at equilibrium, right? It is a 1-to-1 relationship, right? Which means it's the same number. Yeah. Same thing with the chloride. It's a 1-to-1 relationship, same number. Even if it wasn't a 1-to-1 relationship on the right-hand side, whenever you solve for S, it's really the molar solubility of the whole thing is basically what it will be. Let's just say it was 3S on the right, we would divide out the 3 coming back the other way, and it would end up being the same as S. So when you do solve for S, it's really the molar solubility of the whole entire thing. That means that is really 1.26 times 10 to the minus 5 moles per liter of silver chloride. So at this point, I need the molar mass of silver chloride to convert it to grams per liter. So we're going to add these guys together. So silver 107.9 plus chlorine, which is 3545. That's going to give us a molar mass of silver chloride of 143.35 grams per mole. We're going to use that as a conversion factor here. Moles are going to go on the bottom. 143.35 grams of silver chloride will go up on top. And we'll take that times 1.26 to the minus 5. Going to give us a whopping 0.0018 grams per liter of silver chloride, right? That means if I took 1 liter of water or 1,000 milliliters of water, I could dissolve a whopping 0.002 grams, basically, right? Is that a lot? That is not a lot. That is why we consider silver chloride to typically be insoluble under normal conditions, right? But it still has, as you can see here, even something like silver chloride, which is pretty much insoluble. There's still a smidgen of it, right, that will dissolve, right? It's super small amount, and a liter of solution will dissolve. So even anything like I mentioned before that is technically insoluble based on solubility rules will have some degree of solubility, and in most cases it's really small, which is why they're considered to be insoluble to begin with. Any questions on that there? All right, we're laid up there. Let that all digest.